was recorded in front of a live studio audience. Okay. So we're going to do analysis of variance, often known as ANOVA. So we'll just get into the two examples that I have here. Each of these are going to be done with SPSS. This is a statistical program for the social sciences. It's often used in universities. I think we have a free copy here, but you have to go to get it. So you can go to a lab and they'll also have SPSS. So I'm going to be using SPSS, but you can use ANOVA in anything. I've used GeoGebra for ANOVA for personal things that I've worked on, but you can use any kind of statistical software that will have ANOVA. So let's suppose the EPA wishes to test a mileage claim of 4 different brands of foreign compact cars. We're going to select these cars at random from each brand and test it. I'm going to move over here. There's one seat over there, over here, over there. Good. Normally this table is further back. Okay. The mileages are stored in the variable mileage, and the number of car brand is stored in the variable brand. So if you look here on this output, you see how it says brand 1? Okay? Those are not data. I mean, they kind of are, but they're more of a category label. So those aren't quantitative data. All these 4 cars, they come from brand 1. And then these right here are brand 2. These are brand 3. These are brand 4. All right, we didn't label them, Hyundai and Toyota or whatever, but we just label them numerically. So brand 1 has, I'm going to say N1 here, has 4 items. Brand 2 has 6. Brand 3 has 7. Brand 4 has 5. So they all have something different. They have a different number of vehicles in those. That's not going to be very meaningful in what I do because I'm just looking at the computer output, but it would be if we were actually calculating the F statistic. Okay? Okay, so here's what we're going to do. We've got our ANOVA output. And we've got something called a multiple comparisons Bonferroni output. I know, it sounds complicated, or it sounds delicious. Bonferroni always reminds me of like beefaroni from Chef Boyardee. All right, so here's what we're going to look at right here. ANOVA. We need to make sure that we've got some different degrees of freedom in this case. So we have to have independence within each group, similar to when we did the vampires and werewolves one, where we had to have independence within each group, and we also have to have independence between each group. So in an F test, we have different degrees of freedom for within the groups and then between the groups. So we can find that on the chart here, between the groups, within the groups. So we have a degrees of freedom between the groups, we have within the groups, and we have a total degrees of freedom. Here's our F statistic. And here where it says sig, this is our p-value. So these really are the things that we're going to be using. You really don't need much more from there. So I'll pause if you want to take a picture of that. Get my good side. Or don't. Yes.
Are you going to go more into what the difference between within groups?
Yeah. And how we use them in just a second. Okay, so let's go ahead and do our test. So, problem A. Do the data provide evidence of a difference in the mean mileage among the 4 brands? We're going to test with an alpha level of 0.05. So, on your handout, what I've given you is a detailed section of what you need to do for each part. So this is all the stuff that you're going to need to complete problem A. All right? So the first thing you need to do is define your parameters. Since we're using mu1, mu2, and mu3, or even in context, since we have brands, we're going to end up using mu1, mu2, mu3, and mu4. We got 4 brands. So our parameters are mu1, mu2, mu3, and mu4. And we have to define each of these parameters. So what does mu1 represent? It represents brand 1, but more importantly, it represents the mean gas mileage of brand 1, I'm going to say of all brand 1 cars. Remember that mu is our population mean, so we want to say all brand 1 cars. We don't just want to say brand 1. I think that's not enough. Mu is a mean, so we want to say mean. What's mu2? Mean gas mileage of all brand 2 cars. And then just write in the other 2. Perfect. Easy step 1. Step 2 is to write our hypothesis. So we kind of already know what our null hypothesis is going to be, right? We just talked about that. So we're going to write that as mu1 equals mu2 equals mu3 equals mu4. Basically, all of the mean gas mileage are the same. Is everybody clear with everything we're doing so far? Okay, that's a yes, okay. So remember that only one of them has to be off. So I don't want to see this. This is not right. I'm going to write this. Don't write this down because it's not right. Okay, see that right there? That's not correct because we don't want them all to be not equal. We just want at least one of them to not be. So this is in words. Not all mean gas mileage, gas mileages, I guess is, I don't know if that's a word, are equal. Not all mean gas mileages. For, I guess so, that's right, mileages, yeah. So not all mean gas mileages are equal. That would be our alternative hypothesis. So that one's in words. Which is nice because when you get to your conclusion, you're going to base your conclusion on the alternative hypothesis, correct? Yes. Is it hot in here now? Whatever. It's hot outside. Oh, at least we're not in Phoenix. It's like 106 there the other day or something. All right, so here are our conditions. So we've got to do conditions. Our first condition is what? Random sample. Sample of cars is randomly selected. Everyone should get that one right, yes? Always the same thing. Okay, so here is where the assumption of independence comes in. We're just going to go ahead and assume and make this as an assumption, because it really didn't give us a lot of detail here, so I just got to kind of assume that it's true. Okay, so we're going to assume independence between and within groups. Contextually, it just means that no cars were used twice. No gas mileage for one car doesn't affect the gas mileage of another car in one group, and that there's no car that's both types of brands. Does that make sense? So that's contextually what we're talking about. All right, and in order for us to use analysis of variance, we have to assume that the variance is going to be equal. All right, so we're going to assume equal variance among the groups. If the variance is not equal, we can't really do what we're going to do in this one. We've got to use a different test, which we won't be covering in this course. So I think the conditions and assumptions are fairly easy in this case, because you don't have to draw a picture, you don't have to calculate anything, you don't have to make expected values, you just have to say them. Okay? Okay, so next I'd like you to write out the test statistic where K is the number of groups. So go back to, well, a lot of you don't have. So we're going to go up here. K is the number of groups. So how many groups do we have? 1, 2, 3, 4. Okay. So we're going to put 4 there. And the total sample size, 22. And then our test statistic, that if we were looking on a chart, we would have F 4 minus 1, which is
3.
Good math. So quick. These are hard questions, guys. N minus K. Uh-oh, you got to think for a second. N is 22, K is 4? 18. Don't those look familiar? They're right here. 13 and 8. Wait, I said 13 and 8. I meant 18 and 3. Okay. So you asked where these between groups and within groups came from, where the degrees of freedom came from. They come from here. So this is between groups. Oops. Between groups. And this is within groups. So those are the degrees of freedom for each. When we look on an F chart, the F chart is broken up into multiple ways, but we need to have 2 degrees of freedom as well as an alpha level to check. Now, the nice thing about computers is that they give us a significance level. They give us a p-value, the probability, the significance probability of this occurring simply by chance. So we're not really going to need the test statistic because we got the computer output for the p-value. But we're going to write it down anyway just in case we need to. For some reason, a lot of times reports, they like to report that statistic out. So 5.698. So we're going to write that here, 5.698. And then we're going to write our p-value. What was our p-value for those of you that have the handout?
0.006.
Now, for ANOVA, notice here that we have not all mean gas mileages are equal. So we're not going to have a one-tailed or two-tailed test. So we don't have to worry about dividing the sig by 2. We just got to keep the sig alone. Okay, now what do we do? Same thing we did in every test. What do we do now? Compare the p-value to the alpha level. Rejection region is what we did for chi-squared. Yes, we don't have a rejection region here because we're not looking at the F table. Since we have a p-value, it's better just to use the p-value and compare it to the alpha level. Alpha level was, I believe, 0.05. So let's state a conclusion, shall we? We shall. What color should I use today? Pink. Did someone say pink? Oh, I can't use yellow. How are we going to see that? Good choice, though, I guess. Since the p-value of 0.006 is less than alpha, what do we do when it's less than alpha? We reject the null, which means there is evidence. There is evidence that not all gas mileages among the 4 brands of cars is the same. Boom. Yes.
Did you say not all mean gas mileages?
That not. Oh yeah. Duh. Don't want to forget that. That's like the important thing. You know what I mean? Sorry, bad pun. Now that we know that not all of them are the same, we want to take it one step further and find out which ones are different. Because it's not enough to just say, oh, they're not all the same, right? In real life, if we say they're not all the same, we're going to want to know which one is significant. Like which brand out there is really making the things all kind of not different, right? Which one is going to make the biggest significance. So what we're going to do that is we're going to do what we call the Bonferroni multiple comparison procedure. Whew, that's a lot of words. Basically, here's what we're doing. We're telling the computer, I would like you to take every pair of mu's or every pair of x bars and give me a 2-sample confidence interval for every pair. And then tell me what those are. And then I'll just look at the information and I'll tell which ones are significant. That's what we're telling the computer to do. So where we did a 2-sample confidence interval, like we would just take F and S here, and we just look at those two and make a confidence interval, and then say, oh, it's either lower or higher or whatever, we look at it. We're telling the computer, do it for every pairing, so that I don't have to do all that work. The computer says, okay, here you go. And then you got to just check it. So that's what the Bonferroni multiple comparison procedure is. So if we go back up here, we have the output of multiple comparisons. And this right here is brand 1 compared to 2, compared to 3, and compared to 4. Okay? What we're looking for are one of two things. You're either looking for the sig to be smaller than 0.05, or Notice here it says 95% confidence interval. You see that? 95% confidence interval. You want your lower bound and your upper bound to be the same sign. Because if they're the same sign, then that means, since they're both negative, that means brand 1 is going to be lower than brand 4. That's what that means. Okay? Since they're both negative. But if one is negative and one is positive, that means 0 is in here. They could possibly be equal, since 0 is in the interval. Remember we talked about that before when we did the 2-sample t? So when they're both negative, that's good. Well, that's good. That means there's significance there. That means brand 1 is going to be, their mean is going to be less than brand 4, somewhere between 9.7 and 1.1 miles per gallon. So we're going to write that out. Okay? So we're going to write these out. So you're looking for ones that are both the same sign. They're going to repeat too. You see if we compare 1 and 4, go down to 4 and compare to 1, what do we see here? They're both positive, right? And they're the same numbers. See that? I don't need to do this twice. If I've already compared 1 and 4, I don't need to do it again. Okay, so I don't need this one. Is that okay? All right, so let's write this out. Are there any others in there? Do you see any others that are significant? Any other pairings that are significant in that? 3 and 4 right here. Yeah. So we're going to use those two. All right. I believe this is in miles per gallon, yes? It says mileage. So we're going to say miles per gallon. These are old cars. Cars get better than that now. Okay. If you don't have this, take a picture of this now because I don't want to have to come back and go up and down, up and down. All right? In fact, I'll take a picture of it now too. Taking pictures of my computer is weird. Okay. So, determine any significant differences between means, indicating which means are larger than which other means. All right? So if it says larger, we're really looking for two positives. So here's what we're going to say. We are 95% confident that the mean gas mileage of brand 4 cars is between 1.12 and 9.74 miles per gallon larger than brand 1 cars. And, okay, now I could also, if there was a different brand that was greater than something else, I would go here and now say the different brand. But since brand 4 is going to be greater than both brand 1 and brand 3, I'm going to just say and between .24 and 7.75 miles per gallon larger. I don't like the word larger than brand 3 cars. Okay? So we're basically writing the confidence interval statement for any pairing that we see in there. Does that make sense? Yes? Okay, so here's what I'd like you to do. I would like you to do example 2. You can work with a partner or something. I'll give you about, how long do you think it'll take you to do number 2? What? Like 15? I don't think it'll take you. We'll reconvene in 10 minutes. Okay? All right.